Alright. This video is going to work through course pack page 614 with two different examples of arbitrary stress states, plane stress states, that we're going to find the principal stresses. We're going to draw Moore's circle, and we're going to identify the maximum shear stress for these stress states. Maximum shear stress will figure prominently in the next topic, which will be failure criteria. So, if we have this stress state, we have x direction, 8,000 psi compressive. We have no stress in the y direction, and we have a shear stress of 3,000. If we draw this in our simple plane view, we have sigma x is compressive, 8,000. If you're asked to draw an arbitrary stress state, it doesn't hurt to write in explicitly that the normal stress in the y direction is 0. And then we have a positive shear of 3,000. Again, we know to draw the shear in this manner because a positive shear gets drawn upward on the positive x face. So this is a shear stress of 3,000. If instead we drew this on our three-dimensional block of material, you have sigma x, sigma y is 0, and a shear stress of 3,000, and the third sigma z is 0 as well. Alright, so now moving on to sketching the Moore's circle. First thing we need is axes, so we'll grab a couple of those. We see that sigma x is negative and sigma y is 0, so we should know at this point, give myself a little bit more room, to set up the axes with the origin to the right a little bit. Now back to ink. We know that this is our plus sigma axis. We know that this is our positive shear downward, and we plot our 2 points. What are the 2 points that we plot? The first one is sigma x and the positive shear. So minus 8,000 is about here, and we have a plus 3,000 is down, so we'll call this point 1. The second point that we plot is your normal stress in the y direction and your negative shear, and so that is 0 and minus 3,000, so we'll call that roughly there. Now what do? We connect these guys with a line, and the intersection of which is the average normal stress. Then we draw a circle that includes those 2 points, or with the diameter that we just drew, and make our circle clear. And now what do we know? We know that the intersection with the normal stress or horizontal axis is sigma A, and we know that the intersection where tau equals 0, where the shear stress is 0, on the left side is sigma B. How do we identify these locations? We need a few quantities. The average normal stress is sigma x plus sigma y over 2, and that is minus 4,000. So we know that this location is minus 4,000. We know that the radius of this circle, we know how to get the radius of the circle. That's the Pythagorean sum of this side and this side, and that is the square root of the half of the difference term and the shear stress squared. So that is the square root of minus 8,000 minus 0 over 2 squared plus 3,000 squared. And that ends up being 3, 4, 5 triangle, so that is 5,000 psi. So the location of sigma A, the larger principal stress, is the average normal stress plus the radius. So sigma A is minus 4,000 plus 5,000. And looking at that graphically in red, you see we start at the average normal stress and we go a positive distance equal to the radius of the circle, and we end up at sigma A. So that ends up being plus 1,000 psi. Similarly, for our second principal stress, sigma B, we need to take the average stress minus the radius, so that is minus 4,000. In the other direction, so from here, our anchor point at minus 4,000, in the negative direction by 5,000, takes us to minus 9,000 is our second principal stress. Now, to figure out our maximum shear stress, we need to remember that for the plane stress states that we're going to deal with in here, our sigma C is always 0. Sigma C equals 0. You then take sigma A, B, and C and reorder them in value order. So we have 1,000, 0, and minus 9,000. So sigma 1 is the largest of those, is 1,000. Sigma 2 is 0, and sigma 3 is minus 9,000. And then our maximum shear stress, once we've reordered them by magnitude, is always sigma 1 minus sigma 3 divided by 2, which is 1,000 minus a minus 9,000 over 2, or 5,000 psi. Maximum shear stress for this case, 5,000. Alright, looking at another example that will go through the same process. This time our arbitrary stress state is stress in the x direction is 100 megapascal. We have stress in the y direction of positive 50, and we have no shear stress, tau equals 0. So in this case, if we draw our planar arbitrary stress state, we have sigma x tensile 100. We have sigma y also tensile. And again, if one of the stress values is 0, it's probably a good idea to explicitly write that. So our point 1 that we will need for our Moore's circle is 100 and 0, and our point 2 is the stress in the y direction, 50 and 0. This is going to be a slightly different looking Moore's circle than we've dealt with before. So again, we need axes, and we see that both our sigma x and our sigma y are positive, so we're going to skew our axes to have the origin to the left, and we have our x-axis, and we have our shear axis facing shear axis positive down. And now we're ready to plot our 2 points. We have 100 and 0 is our first point, and we have 50 and 0 as our second point. And now what's the rule is to connect those two with a line. A little bit redundant. Let's make it a red line. Nope. A blue line, so that we see what we're doing. And then we need a circle that passes through those points. And with no fill. Well, this is a bit of a trick case. We still need to figure out what our sigma A and sigma B are, and we do that with the fact that sigma average is sigma x plus sigma y divided by 2. So our average in this case is 100 plus 50 divided by 2. So that's 75 megapascal, which is right in the middle. And the radius, by inspection, we can say that it's 25, but by math we say that it is this difference term squared and the shear stress squared. Well, our shear stress in this case is 0, so it's simply the square root of the square of the difference term. So 100 minus 50 over 2, the square root squared is just 25. So in this case, our sigma A is equal to sigma average plus R, which is 75 plus 25, or 100. Sigma X is sigma A in this case. And similarly, sigma B is the average minus the radius. 75 minus 25 is 50. Sigma b equals sigma y in this special case of tau xy equals 0. Said another way, sigma x and sigma y are the principal stresses because the definition of the principal stress is where the shear stress is 0. Because tau xy equals 0. Alright, so now again, to move forward into the failure criteria, we need to know what the maximum shear stress is. To get the maximum shear stress, we use the formula sigma 1 minus sigma 3 over 2. And we need to get our sigma 1, 2, 3 principal stresses. We do that with the fact that sigma A is 100. Sigma B, excuse me, is 50, and our sigma C is always 0 for the cases we'll consider in here. And so if we reorder them, they simply stay in that same order because both principal stresses are positive numbers. So our max shear is 100 minus 0 over 2. Ends up being 50 megapascal.